Hello. Today we have this problem. So we have K is the set of basically unit circle in the complex plane. We have A is the algebra of all functions of this form. I mean, essentially just polynomials defined on the unit circle, because the vertices is e to the power of I data is going to be the sum from n equals 0 up to n capital Cn e to the power of I and data. Alright, now we have to show that, first of all, this algebra separates points on the unit circle, that this algebra does not vanish at any point on the unit circle, that there are still continuous functions on the unit circle that are not in the uniform closure of this algebra. The reason we're promising that is because there's a theorem that states that, well, such an algebra should precisely make it so that all continuous functions on K belong to the uniform closure of A, except there's a missing part where A is supposed to be adjoint, but we're not stated that this is adjoint. So now I'm going to show that there are indeed continuous functions on K that are not in the uniform closure of A, and we're given this hint. Alright. So first let's show that A separates points on K. Well, what we can do is we can literally make a mapping that maps Z to Z, and that's it. Because we can pick n capital as 1, C0 as 0, C1 as 1, and that's it. As for vanishing at no point of K, what we can do is we can make a function f of Z is equal to 1. There's going to be n capital equals to 0, C1 is going to be equal to, okay, C0 is going to be equal to 1. Alright, so these 2 points stand, but nevertheless, there are continuous functions of K which are not in the uniform closure of A. So how do we show that? Well, we're given this integral, which should be true for every f in the closure of A, and how do we show that? Well, suppose we have some sequence of functions f n of e to the power of I data is gonna approach f of e to the power of I data. Then if we were to take the limits of this integral, then this is gonna also approach 0 over here. So they have to show us that there is some function for which this integral over here is not gonna be equal to 0, and we also have to show that this integral is even true for functions that belong to A. Well, how do we do that? Well, first of all, let's copy it over. If we were to look into the sum, this integral can basically be split over into a bunch of other integrals. So let's sum through those integrals from 0 to pi over here, and here we're gonna have e to the power of I times data times n plus 1 d theta equal to 0. Now this n plus 1 is gonna belong to the set of natural numbers excluding 0. Cool. Now what I'm gonna do is I'm gonna show that this integral is gonna be equal to 0. So let's copy it over. And what I'm gonna do is first I'm gonna do a substitution. I'm gonna take data times n plus 1 and substitute stuff. And what I'm gonna get is 1 over n plus 1 times the integral from 0 up to 2 pi times n plus 1 of e to the power of I data d theta. And now what you can do is, again, n plus 1 is not going to be 0, so we don't really care about that. I'm going to show that this integral is going to equal to 0. And how do I do that? Well, I'm going to represent it as a sum from let's take the number let's take letter J for representation. From J up to N, and what we're gonna have is instead of the lower bound, we're gonna have 2 pi j. So the upper bound, I'm gonna have 2 pi j plus 1. And now I'm gonna show that this integral over here is gonna be equal to 0. So the sum is also equal to 0. So we can simply shift the theta here by 2 pi j. And we're gonna have is from 0 to 2 pi of e to the power of I times theta minus 2 pi j, and since the period here is going to be 2 pi, we don't really care about that, and we just get this integral, which is, if you use Euler's certainty, is going to be equal to 0. I think most people know that. And therefore this is going to be equal to 0, therefore this is going to be equal to 0, therefore this is going to be equal to 0, therefore this is also going to be equal to 0, therefore this is going to be equal to 0. Alright, so we have shown this, now let's abuse it. What I'm gonna do is I'm gonna make a sort of weighted function. Let's take some function, call it g of x, and let's define it in some evil way. So we're looking for functions that are continuous on k, so we don't really care about the outside of k, we only need to make it continuous on k. So what I'm gonna do is I'm gonna define it through theta instead of e to the power y theta. When we input e to the power y theta, I'm gonna use theta itself. So when e to the power y theta is close to some e to the power y theta with index 2, that implies that thetas are close enough, given we're working with thetas belonging to interval from 0 to 2 pi. Here let's actually work with another interval. Let's work from negative pi to pi. It's simply more convenient here. You'll see why, yeah? So what I'm gonna do is I'm gonna say, well, let's take the absolute value of theta when absolute value... Okay, no. Let's take the absolute value of theta minus pi over 4 when absolute value of theta is less than or equal to pi over 4, and for the rest let it be 0. So if we were to attempt to integrate this, let's put g here instead. G here is gonna be 0 or a bunch of stuff. So first of all, let's shift everything by pi for convenience sake. So we have from negative pi to pi of g of e to the power of I times theta minus pi times e to the power of I times theta minus pi. Alright, the theta. Now let's bring all of this stuff out. So we have e to the power I theta minus e to the power minus no, e to the power of I theta minus I pi. I pi is going to be equal to, well, we bring out it and we divide by e to the power of I pi, and e to the power of I pi is going to be equal to -1, so we just get a negative integral of from minus pi to pi of g of minus e to the power of I pi times okay, not I pi, I don't know why I wrote that. Minus e to the power of I theta times let me think for a second. Okay, I'm being stupid actually. Let's go back here and redefine stuff for convenience sake, because this fucking sucks. Well, I can just attribute it to the range of 2 pi. I can always just say that this remains intact, and as for this, I'm gonna go ahead and instead of negative pi, I'm gonna map it as 2 pi plus x. Alright, now that we have gotten this out of the way, let's integrate it normally. The minus pi to pi range is useful only for the definition of it. Other than that, it really sucks, apparently. So what we have here is integral from 0 to pi over 4 of what do we have here for the definition of g? We have well, here's gonna be just data times e to the power of I data d data plus the integral from 7 pi over 4. No, yeah, okay, 7 pi over 4 to 2 pi. Now we're to map it back. So some mapper, let's call it t of x is going to be equal to this. Now let's find the inverse. X is going to be equal to 2 pi minus t of x. Okay, no, t of x minus 2 pi. Right, so what we have here is 2 pi minus data times e to the power of I data d data. Alright, now what I'm gonna do is let's work with all of this stuff. So first this thing over here, let's actually take the cosine of all of this. That's the only thing relevant here. Let's take the real part. So what we have here is the integral from 0 to pi over 4 of data cosine data d data. Next we're gonna have plus integral from 7 pi over 4 up to 2 pi of 2 pi minus zeta times cosine of theta d theta. Again, we're working with the real part here, purely for convenience sake, because again, what we have to show that it's not equal to 0, and the real part will be sufficient. So here I'm gonna do a substitution for 2 pi minus theta. So here we negate this. Here we will have 0. Here we'll have pi over 4, and then we can just swap the bounds. So from 0 to pi over 4. Now recall the substitution to pi minus 0, minus theta. In cosine we can get rid of the 2 pi, and then minus theta is going to be the same as cosine of theta. So what we get is just theta here. Alright, so we just get 2 times this integral. Now if you were to carefully look at that, theta is always going to be greater than or equal to 0 here. Cosine of theta is going to be greater than or equal to square root of 2 over 2. Now what we can do is we can just pick some arbitrarily small number. Let's pick 0.05, and we know that the integral from 0 to 0.05 0.5 of this expression is going to be greater than or equal to 0. And as for the other one, the rest of it from 0.05 to pi over 4 is going to be greater than 0. Then we sum it up, so it's going to be greater than 0. So this thing is greater than 0, so this thing is not equal to 0. Alright, I hope this wasn't too lengthy, and I also stuttered a lot, sorry for that, but yeah, here we go. That's it for today, bye.